So you hear the term AI learning thrown around all the time, right? But what does that actually mean? How does a pile of code go from being, well, just code, to something that feels like it can understand the world? In this explainer, we are going to pull back that curtain. Let's get into it.
I mean, really think about this for a second. You don't sit down and write code that says, if it has pointy ears and whiskers, it's a cat. No way. You just show it a ton of pictures of cats and dogs, and somehow it just gets it. This is the central mystery we're going to solve today, and the answer, it turns out, is pretty brilliant.
You know, the craziest thing is, the inspiration for all of this is us. It's our own brains. When we learn something new, the connections between our brain cells, our neurons, literally get stronger or weaker. Well, an artificial neural network does pretty much the same thing. It has these digital connections between artificial neurons, and each one has a number on it, a weight. And when the network makes a mistake, it just tweaks those numbers. So for an AI, learning is really just one giant continuous math problem.
Okay, so here's our game plan. We're going to start with the basic anatomy of an AI's brain. Then, we'll see how it scores its own guesses, how it knows when it's wrong. From there, we'll look at how it finds the path to a better answer, uncover the clever trick that makes it all possible, and then finally, see how this all holds up in the real world.
All right, first things first. Before an AI can learn a single thing, we've got to build it a brain. So let's take a look at the basic anatomy.
So every neural network, at its core, has these three main parts. You've got the input layer. Think of it as the front door, where the data comes in, like every single pixel from a photo of a cat. Then you have the hidden layers. This is the real powerhouse. This is where the magic happens, where it chews on the data and finds patterns. And finally, the output layer gives you the answer, spitting out something like 98% sure that's a cat. It's a one-way street. Data flows in, gets processed, and a decision flows out.
And here's the key takeaway, the absolute heart of it all. Learning, for an AI, is just the process of tuning. The whole game is about adjusting millions of tiny digital knobs, these weights and biases, on the connections between the neurons. The goal is to find that one perfect combination of settings that gets the right answer as often as possible. Okay, but wait, how does the network even know which way to turn those knobs? How does it have any idea if its guess was good or bad? Well, first, it needs a way to measure just how wrong it was.
It does this with something called a cost function, but honestly, the best way to think about it is as a wrongness score. It's a simple bit of math. It looks at the network's guess, say dog, and compares it to the correct answer, cat, and spits out a number. A really high number means, whoa, you are way off. A number super close to 0 means, nice, you nailed it.
And that right there, that single sentence is the entire goal of AI training. Everything else, all the complicated algorithms and computing power, it's all dedicated to this one single mission. Get that cost function, that wrongness score, as close to 0 as you possibly can.
So, we have our score, we know how wrong we are. Now, how do we actually get less wrong? This brings us to the real engine of how AI actually improves.
It's an algorithm called gradient descent. Now, the name sounds super technical, right? But the idea behind it is almost ridiculously simple. A gradient is just a fancy word for the direction of the steepest slope. So gradient descent literally just means find which way is downhill and take a step. That's it. It's how the network systematically walks its way towards the lowest possible error.
This analogy just nails it. Picture yourself as this hiker. You're standing in a huge valley, but it's completely filled with fog. You know the lowest point. The best answer is down there somewhere, but you can't see it. So what do? You just feel the ground right under your feet, you find the direction that goes down the sharpest, and you take one small step. Then you stop, feel the ground again, and take another step. If you do that enough times, you are guaranteed to eventually find the bottom of the valley. That is exactly what gradient descent is doing inside the AI.
Now for the last big piece of the puzzle. Okay, we're walking downhill. But the network has millions of those little knobs, those weights. How does it know which specific knobs to adjust? How does it know which ones were most responsible for the mistake? This is where the real genius comes in. It's an algorithm called backpropagation, and just like the name says, it works backward. It starts with the final error, that wrongness score, and it works its way back through the entire network, layer by layer. It's kind of like an internal investigation, using some clever math to figure out exactly how much blame to assign to every single connection for that final mistake.
So let's put it all together. This is the whole shebang, the full training loop. Step 1, a photo goes in, a prediction comes out. That's the forward pass. Step 2, the cause function tells us how wrong we were. Step 3,
Backpropagation goes backward and figures out who to blame. And step 4, gradient descent makes tiny little adjustments to those weights to do better next time. And the key thing is, this loop runs thousands, even millions of times, getting a tiny bit smarter with every single pass.
So, that's the beautiful theory. It's elegant, right? But of course, when you take this stuff out of the lab and try to use it in the real world, well, things get a little messy.
The single biggest headache for anyone working in AI is something called overfitting. This is what happens when a model gets too good at the data you showed it. It's like a student who doesn't learn the concepts, they just memorize the answers on the practice test. Then, when the real exam comes along with slightly different questions, they completely bomb it. An overfit AI is a useless AI.
So how do you fight back? Well, data scientists have a whole bag of tricks. They can just stop the training early, before it starts to memorize. They can prune the network, like a gardener snipping away useless branches. They can even add a penalty that punishes the model for getting too complicated. All of these techniques have one goal: force the model to understand the general patterns, not just memorize the specific examples.
But all these fancy algorithms and clever tricks, they mean absolutely nothing without the most important ingredient. It really is true what they say. Data trumps all. You can have the most powerful AI model on the planet, but if you feed it garbage data, you're going to get garbage results. Every single time.
And if you need proof, just look at this number. People who do this for a living report spending up to 80% of their time not on designing cool AI, but on the grunt work of collecting, cleaning, and preparing data. That tells you everything you need to know about what really drives success in this field.
And all these core ideas we just walked through, they are the absolute foundation of the big AI models you hear about every day. A GPT model is so good at writing because it's been trained on one simple goal: predict the very next word in a sentence. A BERT model, on the other hand, is great at understanding what you mean because it's trained to look at the entire sentence at once, forwards and backwards, to get the full context. It's the same fundamental learning process, just pointed at a different target. So, there you have it. We went from a simple question about cats and dogs all the way to the core engine that powers things like GPT. We've seen that AI learning isn't magic. It's just math. A simple, brute force process of making a guess, measuring how wrong you were, and taking a tiny step in the right direction, repeated millions and millions of times. Which leaves us with a much bigger and way more interesting question. Now that we understand how these things learn, what on earth should we be teaching them next?